So welcome back. We just made it to the end of the chapter 14, solutions. So last time we met, we began talking about colligative properties, and we covered vapor pressure, and we saw that when you take a pure solvent and you add something to it, making a solution, we saw how the vapor pressure is going to decrease, and we saw that this was due to the new intermolecular forces that are part of the mix now. So stronger intermolecular forces, like ion dipoles, for example, harder for the molecules of the solvent to escape, so lower the partial vapor pressure of the solvent, because it could be that the solute is also volatile. So if both of them are contributing to the vapor pressure, we are only talking about the partial pressure of the solvent, not the solute. Most of the time, the solute is not going to be volatile. So with that said, we are continue doing colligative properties. And now we're going to be talking about boiling point elevation and freezing point depression. Let's make sure that we understand this. So boiling point, how much energy does it take for all the molecules on the solvent to be able to escape into the gas phase? That would be the point at which you get boiling point. So once more, the solvent, which is the pure solvent, will evaporate at a certain temperature. When you put a solute on it, now you are creating additional intermolecular forces, which may which force you to have more energy to reach the temperature at which you can disrupt these additional intermolecular forces. So therefore, putting a solute in a solvent creates an increase in the boiling point. Therefore, boiling point elevation. How do we understand the freezing point depression? So for example, water freezes at 0 degrees Celsius, but if I have a solution, an aqueous solution, a solution with water where I put a solute, now you can have ion dipoles interactions there. Since you are dissolving something in the solution, you're going to have the ions with the hydration cages. So if it was the solvent by itself, the molecule will have to slow down so they can find the right orientation where partially positive meets partially negative, and they start coming together. Now you have a solid on the mix. Now the water not only has to organize with itself, it will also have to organize the hydration cages with others. So they're going to have to even slow down further to be able to get the proper position so they can begin constructing the lattice to create the solid. So the fact that the molecules have to slow down even more indicates that the freezing point is going to be even lower than before, which is what we call the boiling point depression. So all that based on intermolecular forces and the organization that is required to create a solid or a lattice for the solid. So we're talking in terms of the solvent. The solvent is the one that is being affected because you added something to it. So through centuries, probably, we have been measuring the properties of those solvents, and we have come up with constants for boiling. So this will be the constant for the boiling point elevation, and you will also see the constant for freezing or fusion. So each particular substance will have a different value, and this value is going to be based on the temperature at which the process will happen, based on the molality. Remember that lowercase m is not mass, is not meters, is molality in this case. And molality is nothing more than the moles of the solute over the kilograms of the solvent. And this is important. Why is this term important in determining the change in the boiling point in this case? because the more solid you have, the more intermolecular forces are going to be present. So the bigger the change will have to be. For example, what is delta TB? The, the change in the temperature of boiling is going to be equal to the temperature of boiling of the solution, the one with the solute, minus the boiling point of the solvent. So in the case of water, water boils at 100 degrees Celsius. So since we have new intermolecular forces, let's say arbitrarily, let's say that now the solution boils at 103. So what we're finding with the formula is the change in boiling point, which is going to be 3 degrees Celsius. So that's what you're finding, but you have to be aware that that's nothing more than the new boiling point of the solution minus the boiling point of the pure solvent. So once more, why is molality important? Well, because molality implies that you are getting more solute in there. So as this gets bigger, right? The change in the boiling point temperature should get bigger. More particles, more intermolecular forces, the bigger the change in boiling point. And the same logic applies for the for the freezing point depression. Freezing point depression is going to be the change in the temperature of freezing equals the molality times the K, not the KB, but the KF. So you're going to need another table. And it gives you this normal boiling point. So you're finding, remember, delta TF is going to be the freezing temperature of the solution minus the freezing temperature of the pure solvent. So that's kind of a nice way to predict, based on how much you put in there, how much lower you're going to have to be in terms of freezing. So if you are civic engineering, trying to decide, looking at the weather and saying, wow, the temperature is going to go down to minus 3 degrees Celsius tomorrow, and it's going to be raining. So the moment that water falls, it's going to freeze, and I'm going to have a lot of accidents. You can say, well, let's get ready for that. Let's make sure that water doesn't freeze unless it hit 106. So if I have 1 kilogram of water, how much salt do I need to put on that particular mixture? And the engineer have a lot of formulas that I am not even aware of. How much salt will I have to put in the water to make sure that it doesn't freeze until 106? That way my roads are going to be clean, even if it goes to minus 3. So this is this has very practical applications. From the point of view of a chemist, this is a powerful tool because it allows you to find molar mass. What do you mean molar mass? Well, you're going to be using molality, right? And molality is moles of the solute of the kilograms of the solvent, right? But what is moles? Mole is nothing more than the mass divided by the molar mass from the periodic table, right? Over kilograms of the solvent. So if I make a new compound, I don't know exactly what the formula is, I don't know anything like that. I can take that compound, I can dissolve it in water, I can measure, I know that the freezing point of water is 0 degrees Celsius. I can measure exactly how much of the new compound I'm putting there. I can measure exactly the amount of water that I'm putting there. I can find my change in freezing. I can find this value from the table. and I know that molality is mass divided by molar mass divided by kilograms. So this I get from the table, this I can measure, this I can measure the change with a thermometer, so that will allow me to find the molar mass. So this is an excellent way to find the molar mass of a new compound that I just created. And if you remember for Chem 1411, I can take that compound, throw it on a machine, and it will give me the percent of carbon, the percent of oxygen, and so on. With those percentage and the molar mass, I can find the molecular mass. So this is a very powerful tool. And I can do it with the change in freezing, or I can do it with the change in boiling. The change in freezing is a lot easier to measure. So this is a formula with a lot of applications. So let's see how we can use it on a problem. So let me clear the screen a little bit. So how do we use this on this problem? For example, calculate the freezing point and boiling point of a solution. So I'm looking for the solution. So I'm looking for the freezing point of the solution. And I'm looking for the boiling point of the solution. Containing 10 grams of naphthalene, and the formula is given there, in 100 milliliters of benzene. So based on those amounts and based on the way it's the sentence is phrased, I would say this is my solute. And if you don't know how I know this is the solute, make sure you review the first recording, 14A, and this would be my solvent. So this is one of the first things you're going to have to be able to do. So, and benzene has a density of that much. So my solvent is benzene. So on this table, which is the table for my solvents, I had to find benzene. So I know my Kb for benzene. So let's take this problem into a place where we have more space. So let me clear first. I already know which one is my solvent, which one is my solute. All I need from the table is this part. And let's get us a little bit more space. So that's the problem we're working on. So if I want to find the temperature of the solution, I know that minus the temperature of boiling of the solvent equals delta T of boiling, or boiling point elevation. So I know that that's the boiling point of the solvent. That's right there. If I can find this, then I will be able to find that, right? So if I know this and I know this, I can find my unknown. So delta T, I'm going to find it from here. So delta T of the boiling point elevation is going to be equals to the molality. The molality is the mass of the solute divided by the molar mass divided by kilograms of the solvent, right? So that's molality. Do I know my Kb? Yeah, my Kb is right there. 2.53 degrees Celsius over molality. So delta Tb, then it would be the mass of the solute, which is 10 grams, right? Divided by the molar mass of the solute. I know the formula, I know my periodic table, right? So I'm gonna round the numbers. So I have 10 carbons at 12.0 grams per mole. And I have 8 hydrogens at 1.0. So that's going to be 128 grams per mole. So I know my molar mass, 128 grams per mole. So that's how many moles I have divided by the kilograms of the solvent. Well, the solvent is benzene. So my solvent is benzene. I'm given the milliliters, but I'm also given the density. So 100.0 milliliters. I do cubic centimeters is the same as milliliters, right? 0.877 grams. So that will give me the grams of the solvent, but I do not want grams. I want kilograms, right? So 1 kilograms equals 1,000 grams. And that will give me my kilograms of the solvent. When I put that in there and I multiply it by this number, that should give me my delta TV. Remember, this is not a math class, so I'm just explaining the process, not the math. So once I calculate this, like I told you from here, this is nothing more than this value. And once I solve that, I will get this number. And this number, that's what I'm going to find, is going to be equals to this minus that. And this is nothing more than this value there, the one given on the table. So if I know this and I know this, which I just found there, right, I can find that. So all you have to do is the math, which you should master that math. That's just a basic arithmetic. If not, come to my office so we can work on it. And that's how I would find the boiling point of the solution. If you get a boiling point less than 80.1, you did something wrong, because we're looking for boiling point elevation. The boiling point of the solution should be higher than the boiling point of the solvent, which is benzene. If we were doing a freezing point, then it should be lower, because we're looking for lower freezing point depression. So this will be your daily work. Remember, is repeat this, go back and forward, rewind, stop. If that still doesn't do it, go into the canvas and go into the tutorial videos, and you will have somebody else in there with a different style of explaining this, which probably is better for you. Or go into the textbook, and the textbook shows you through the chapter, step by step, on how to do it. Combine all those three sources and whatever you can find on the internet until you get the knowledge that you're trying to get on your own. I'm just coaching you. Remember that. And this will be your daily work. And then we can continue doing problems the same way. The only different thing here would be that now on the, let me go back to this daily work. Let me point out on this daily work. This daily work is pointing out that you're dealing with a non-electrolyte. So let's talk about that before we move forward. If I take NaCl and I put it in water, I'm gonna get Na plus aqueous plus Cl negative aqueous, right? The formulas for boiling point elevation and freezing point depression, they deal with the molality of the solution, which depends on the amount of solid, right? So if you have an electrolyte, something that can break apart, you gotta be careful, because if I have 3 moles of this, now I'm gonna have 3 moles of this and 3 moles of that. In terms of molality, we don't care about what is what. We just care about the amount of moles of particles that we have. So in reality, on that solution, you're going to have 6 moles of ions. We don't care if they're positive or negative, but you got 6 moles. So that's what this formula is showing for. So a small variation of the formulas I just showed you is when you have electrolytes. And when you have electrolytes, you're going to have what we call the Van Hoff factor. Van Hoff factors, a very rough approximation is, if I have NaCl, the Van Hoff factor is going to be 2. If I have sodium phosphate, the Van Hoff factor is going to be 4. If I have magnesium chloride, the Van Hoff factor is going to be 3 because it's going to break into 1 magnesium and 2 chlorides. So the Van Hoff factor, very rough approximation, is the number of particles. When we go into the lab and we calculate the Van Hoff factor, it could be probably 275, 3.1, but very rough, you can just say it's the number of particles, and that's what we can use on this course. So if you have an electrolyte, if your solute is an electrolyte, be aware of the Van Hoff factor. If you're dealing with a non-electrolyte, then your formula, the Van Hoff factor is just 1 because it's not breaking, and you don't even show that on the formula. So electrolytes, be really careful. And then we have something else. So before we leave boiling point elevation and freezing point depression behind, there's another colligative property that is super important, and that's going to be osmotic pressure. So let's make sure we understand what osmotic pressure is before we go any further. So what is osmotic pressure? So imagine you have a pure solvent, let's say water, and you have a semi-permeable membrane splitting the container into 2 areas. A semi-permeable membrane would allow the movement of the solvent back and forward. So if you have water, because the same water is going back and forward on equilibrium, you are not going to see any changes. What happens if I put sodium chloride in there? When I put sodium chloride in one of the sites, now you're going to have not just water, but other particles. And the concentration on this side is going to go higher. On this side, you cannot even talk about concentration because it's just pure solvent, right? However, since you have a semi-permeable membrane, the system will try to establish an equilibrium between both sides. So now you're going to have osmosis and dialysis happening at the same side. So some of the sodiums are going to come there, but it's going to reach an equilibrium on a point where the water you have, most of what you have is water. So the water is going to start transferring to where the salt is more concentrated to try to level the concentration of the salt. So if more water comes over here, what you're going to see is, so we know that those ions are in there. So it's just like a glass of water. You don't see the ions, right? But you know they are in there. So the water is moving toward where you have more salt to try to level the concentration on both sides. So to do that, water will have to travel to one side more than the other. So what you're going to see is that the level on one side is going to go up because more water went over there. Now those particles that you have there, they're going to try to move. But in addition, the amount of water here is higher than here So based on gravity, this is going to be pulled down. When this gets pulled down, those particles are going to put even more pressure on the wall. Some of them are going to go through. Others are just going to put pressure on the wall. So that's what we call the osmotic pressure, because you have osmosis happening, movement of water, that increases the level on one side. The shear property of weight pushes down, creating more pressure on the wall, and that's what we call osmotic pressure. So does it make sense that as I increase the solute, the osmotic pressure should go up? Do you have more particles now? Yes, it makes total sense. So that's why this formula is expressed like that. Osmotic pressure, which is a colligative property because it changes when you add solute to it. These are physical properties, they should not change, but the moment you add a solute to it, they change. It's going to depend first on how many particles you're putting, the Van Hoff factor. It's going to be based on the molarity, the moles of the solute divided by the liters of the solution. So the more concentrated it is, the more pressure it's going to put. And then we're going to use the temperature, right? Because if the particles are pushing against the wall, the faster they move, the more pressure. So as the temperature increases, they're moving faster. And then to make everything match, we have, on this case, a constant will work. And like in nature, there's some specific numbers there that make everything work. So this is one of those constants that make everything work. This is the gas constant. We're not dealing with gases here, but it still works. So this number is special in nature. So what is R? R is 0.08206 liters, atmospheres, moles, Kelvin, or 8.31 joules, moles, Kelvin. So that tells you the temperature is going to have to be Kelvin. We're dealing with osmotic pressure, so which one of these R deals with pressure? The 0.08206, right, is dealing with atmospheres. So we do not use this R, not for this problem. This is the R that we use. So nothing more than knowing the Van Hoff factor, right? NaCl equals 2, aluminum nitrate equals 4, and so on. And knowing the concentration, which is going to be given by moles divided by liters. So that's the other colligative property that we needed to cover. So these problems give you the molality. On these problems, we need molarity. So you saw at the beginning of this chapter the techniques that we use to go from molality to molarity. You saw also we can take a percentage and change it to molarity also. So this is nothing more than applying what you already learned on the previous chapters. And with that said, that would be your daily work. So a percentage. So how can you change percentage into molality? Because you're dealing with boiling point, right? So that would be this formula here. I mean, that formula there. So molarity and molality. For osmotic pressure, you're going to need molarity, which you already have. That's no problem there. Melting point is the same as freezing point. Remember that. And you are given the molality already. So the percentage is the one that is going to require a little bit more effort, because you're going to have to change from percentage to molality to be able to do the problem. And with that said, we just finished covered colligative properties. On the previous recording, we did vapor pressure. Now we just did boiling point elevation and freezing point depression. And we also cover osmotic pressure. So like I said before, I am not looking to see if you know how to do the math. I am looking for you to understand what the formula gives you. If I say delta T B, you should know that that's boiling point elevation, which means the solution boiling point is higher than the pure solvent. You should know that delta TB equals temperature of boiling of the solution minus temperature of boiling of the pure solvent. And you don't have to memorize this formula. I will give it to you. You know that's the molality times the KB. And it wouldn't hurt to put the Van Hoff factor in there. If you're dealing with electrolytes, you should know what the Van Hoff factor means. And important to know that molality equals moles of the solute over the kilograms of the solvent. Important to know that that is the same as moles of the solute is nothing more than the mass of the solute divided by the molar mass. That is not going to be on the packet because you should know that from Chem 1411 divided by the kilograms of the solvent. So you should be able to take the molality and break it all the way to this to find any of these three. So that's the way I want you to study these formulas, not to try to get a number or to understand what you're dealing with and how you can use it. Like, for example, to prevent the water freezing on the road, right? Or to find the molar mass of something so you can find the molecular formula. And with that, we come to the end. So, like you already saw on test number 1, every single objective that you see on this list at the beginning and at the end of the chapter is going to be on the test. So this is your review. This is how you study. Get a study group, quiz each other until you understand every single concept in there. So until the next, see you later. Take care.